So now it seems like leaving things incomplete, but actually the description of the Quasi-Newton method is complete. Why? Let's try to just quickly summarize how we would start. So at step 0, what do I like with any algorithm? What is step 1? Pick a starting point. Pick some x0. Now notice this BFGS relation. Can I compute it from scratch? For example, at k equal to 0, what do I need in order to kickstart this expression? I need h0. Somehow you need to tell me h0. So I am going to say pick h0 and estimate h0. Okay. So maybe you need to pay a one-time price to get h0. Okay. Next, what would I do? Correct, that is one choice. If it were very expensive, then I may need to do some approximation there also, but otherwise h0 could come from the Hessian. Okay. Then what do I need to do? I need to go from x0 to the next place, what do I need? I need alpha, I need p, right? So for alpha, what is our standard procedure? Inexact line search with Wolf conditions. Okay, I got it. Do I know which direction to go to? I do. How do I know it? I calculated it right at the beginning, right? So direction is simply pk is equal to minus hk grad of k, right? So if you notice right at the beginning, where did it go? Yeah, here. Bk inverse grad of k. Now Bk inverse, the notation I have got for it is h. Direction is this. Okay. So this will allow me to go to the right. So that means go to xk plus 1, right. What should I do next? Computer? Okay, before I do that, should I do something else? I have moved to the next point. Correct. We should always have a check for convergence, right? So I would say, for example, check norm of grad of k. Okay. If it is low enough, end. Else, what should I do? Should I go to step 2? Step 3, what should I do? I need to update my h, because unless I update my h, I cannot compute the direction which is sitting in step 3, right. So here is else, use BFGS to get hk plus 1, then 2 and 3, right. So that's our Quasi-Newton method. Did I ever need to compute a Hessian? I never needed to compute a Hessian, right, because my BFGS relation, for example, what does it need? This guy is coming from the previous step, right. Sk is coming from what? The difference of the previous two, right. Sk was defined as, we had it over here, right, difference of iterates, xk plus 1 minus xk. So if I know where I am and if I know my previous step, I can calculate s. Similarly, y I can calculate, right, and so I have my sk, I have my yk, and what else? Rho is given over here. So basically, this whole expression can be computed. SK transpose, quick check. What is SK transpose? Scalar vector matrix, rank 1 matrix, right? And so this entire expression is a matrix. So given the previous HK, I can update this, calculate the new H, and move on. Okay. You will find actually there is something even more popular than BFGS in the relation, and particularly in MATLAB you will find there's something called LBFGS. L stands for a low memory version of the BFGS, which is extensively used in optimization, where you do not want to do, where you want to do Quasi-Newton methods. This is one flavor. So these letters BFGS, they stand for the founders of this method. Okay. So the one thing that we left kind of hanging is this over here. We never, so far I have not shown you or given you a guarantee that this B that I get is going to be positive definite. BFGS is fixing the remaining sort of degrees of freedom, but how do I ensure that it is positive definite? That is still left to me. Okay. Now it turns out, we'll work it out right now. Our Wolf conditions, they save the story in innumerable examples, and this is one more of them. Okay, so it's a very cute little result. Let's show it to you over here. It says that if alpha k satisfies the Wolf condition, in particular the curvature condition, then bk plus 1 is always a surprising result, right? And it's not only is it surprising, the proof is also very simple. So what was the curvature condition? If you remember the English, you will be able to tell. What was it? So remember we had something like this. So what did it say? So if this was my phi of alpha, I said that the slope at phi dash of alpha should be less than what? C2 times phi dash of 0. If you remember it in words, you will always remember what is going on over here. Now phi dash alpha, remember the way I have drawn this slope over here, drawn this graph over here, phi dash is positive or negative? Negative, right? So, and this is the curvature condition, not the strong curvature condition. So, there is no absolute sign over here. So, in order for me to write down this over here, I had to put a minus sign. So, phi dash alpha was what? Grad of xk plus alpha pk transpose what? Pk, right? And similarly for this we can write it over here. But in order to get the slope over here with a positive sign, I had to put a negative. Okay, that's how we had worked it out. So basically what this would translate to is grad fk plus 1 transpose pk is greater than or equal to C2 times grad fk transpose pk. If you are a little rusty on your curvature condition, this was a quick recap. Okay. Now, supposing I subtract grad fk transpose pk from both sides, what will I get? Left hand side is going to give me grad fk plus 1 minus grad fk transpose times pk greater than equal to, I am going to write this as 1 minus C2 into minus 1 into grad fk transpose pk. Okay. It should be C2 minus 1, I am writing it as 1 minus C2 into minus 1. Okay. What is grad? Is this okay with everyone? We just subtracted over here, subtract grad fk transpose pk from both sides. What is this left hand side? Grad fk plus 1 minus grad f is what? Yk. So this is yk transpose pk. Right, so when I wrote this expression, the first expression, it was intuitively that this slope should be less than, the slope at this point alpha should have reduced to less than C2 times the original slope.
Okay, the magnitude of the slope
magnitude, right? And to get the magnitude, I multiplied by minus sign to get it as a positive number. Correct. These are all valid descent. This is a valid descent direction. That is the intuitive way to remember it. Right. Okay. So I get yk plus yk transpose pk on the left hand side. What is 1 minus c2? Is it greater than 0 or less than 0? It's greater than 0, right? Because c2 was between 0 and 1. So this is greater than equal to 0. What about this guy? pk is a legit descent direction. So grad of k transpose pk is less than 0 multiplied by minus 1. This is greater than equal to 0, right? So if I multiply this by a positive number alpha k, what will I get? Right? If I multiply by alpha k, I'm going to get yk transpose alpha k pk. But alpha k pk is nothing but xk plus 1 minus xk, which is sk. So this is yk transpose sk, and we have seen that this is greater than equal to 0. Right? Now, if you look back at what we had said over here, sk plus 1 transpose yk should be greater than 0, then this is going to be positive definite. Sk transpose yk, do I have that? Yk transpose sk, same thing, right? So the secant equation was bk plus 1 transpose sk is equal to yk, right? And then when I left multiplied by sk transpose, I got sk transpose bk plus 1 sk is equal to sk transpose yk, and we just showed that this is greater than 0. Actually, there's one, it should not be, yeah, this is greater than 0, and it's a legitimate descent direction. Therefore, this angle cannot be, they're all strictly greater than, because C2 was in the open interval 0 to 1. So this term cannot be 0. So it's not greater than equal to, it's greater than. Okay. So implies that bk plus 1 is correct. Okay, so right, so let us see. Well, it is at least true for sk, right? And do I need it? Actually, here we need to look at the proof. Do I need it for other vectors? That is something to think of. Okay, I'll think about that. It's not clear to me looking at this BFGS relation whether or not that would be the case. Maybe it will be. Yeah, we need to look at this a little bit more. So if I start with a positive definite HK, will HK plus 1 also be positive definite? Yeah, I don't want to make a casual comment. Let's look at this a little bit more carefully. The same matrix is away. Okay. So Wolf conditions have helped us earlier also, it's helping us now also. So whenever you do a backtracking line search, it's always a good idea for the termination condition of the backtracking to be one of the Wolf conditions. Right. So this essentially completes our whatever description that we needed to learn about the Quasi-Newton way, Quasi-Newton method, right? The recap is over here. We know we have all the pieces in place. What is the design choice, or you can say the place where you have room for innovation? Could replace BFGS by something else. The secant equation is going to be there, that doesn't change. The remaining n squared by 2 minus n relations are going to come from something else. BFGS is one example of it. So, when you, this is another something for you to look at in your course project, choices, different ways of implementing Quasi-Newton. This is one example. Okay. And as we said, this is superlinear in convergence. Okay. And as far as coding goes, they are all relatively similar complexity. This is in fact simpler to compute than Newton because there is no Hessian computation involved. Right. Okay. So, what we have done, I mean, if we just take a quick recap of the different line search methods that we have done, we have started with steepest descent, we looked at it in great detail, we moved to conjugate gradient, and we moved to the nonlinear version, which is nonlinear conjugate gradient, and then we looked at the Newton method and the Quasi-Newton method. So, in terms of tools of optimization, you've got a nice range of tools available with you. Depending on how difficult or computationally challenging the problem is, you can choose one or the other method.